All dimensions of every drawing will have a tolerance. The definition of tolerance is the permissible variation in form, size, or location. No two parts are identical. If you measure precisely enough, you will find variation. The mathematical definition of tolerance is the upper limit minus the lower limit. Tolerance by definition will always be a positive number. You might have a negative deviation, but the tolerance will always be positive. Here you see a shaft above a hole. Both the shaft and the hole have a tolerance given and shown using the limit method. You should be able to determine the tolerance for each part. You might see tolerance given as bilateral or unilateral tolerances. Bilateral allows deviation in both directions, where unilateral only allows the variation in one direction. One thing you want to watch out for is tolerance accumulation. This happens when parts are poorly dimensioned and will cause parts not to fit together. Look at this example. Holes are located using a chain or continuous dimensions. Each dimension has its own allowable tolerance. Therefore, the hole on the far right could be 4 times the intended tolerance value, larger or smaller, which would prevent the part from fitting or performing correctly. Baseline dimension is a better solution. In this example, the tolerance amount is applied properly to each hole location as intended. Tolerances are often given as a general note and in many cases found in the title block information. Tolerances can also be provided as a local note with an individual dimension. Here, the tolerance is shown using the limits method. This drawing is using the deviation method to display the tolerance. In AutoCAD, to display a tolerance on a dimension, adjust that dimension's property, changing the tolerance display to your desired method and adjusting the tolerance limit lower and limit upper values. Using Inventor is very similar. Here is an example of symmetrical limits and deviation tolerance display methods. I want you to use the limits method on your projects. You can also set the tolerance to display using your Dimension Style Manager, but note this will add tolerance values to all of your dimensions. In this example, A is shown with a deviation tolerance. Determine the maximum limits and minimum limits and then the tolerance of the dimension. Now that you have your mind wrapped around tolerances, we want to shift gears into fits. Fits are pre-designed combination of tolerances that allow mating parts to achieve design criteria. There are only three types of fits between parts. Clearance fits means there will always be space or clearance between the two parts. Interference fit is the opposite. There is no space, but the two parts are interfering or overlapping one another. How is this achieved, you ask? Hydraulic presses, thermal fitting, and big old hammers are used to make interference fits. The last fit is transition fits. Transition fits could have clearance or interference depending on the actual measurements of the parts. Tolerances are controlled to allow parts to fit together. There's three types of fittings: completely interchangeable, where all the parts will always work; fitted assembly is where one or two or more parts are actually hand fit to mate together; and then selected assembly is where you go through a quantity of parts until you find two that will work. Obviously, completely interchangeability assembly is the better solution for mass production. This is a good exercise to practice determining the tolerance of a dimension and the minimum and maximum clearance between the hole and the shaft. In this example, which is similar to your first drawing project this week, there is a 1.5 diameter hole and we need an RC2 fit. RC is a running clearance fit, which means there will always be space or clearance between the hole and the shaft. Stop right now and look at the fits table on the course content page of Blackboard. Find the row of data that corresponds to 1.5 diameter and determine the hole tolerance amount from the RC2 column.